In the previous video, we understood how the resting membrane potential is maintained in the cell and the difference between a graded potential and an action potential. Now we are going to understand the generation of the action potential. A resting membrane potential of minus 70 millivolt is maintained in a neuron. So the inside of the membrane is negative, while the outside is positive. The cytosol and the extracellular matrix, they have equal number of positive and negative ions and therefore are neutral. If this is your cell membrane, it will have two ion channels. These both, they are ion channels. These are the sites where ions will move across the cell membrane. This one here is the sodium ion channel and this is the potassium ion channel. In these two ion channels, there are gates that will either close it or open it. In the sodium ion channels, there are two gates. This one is the inactivation gate and this one here is the activation gate. So this will open when we have to activate this channel and this will close when we have to inactivate this channel. The potassium ion channel is a simpler one. It just has one blockage that will either open or close this channel depending on the state of action potential. This brings us to the three phases of this action potential. The first one is the depolarization one. Depolarization means that this potential will decrease or the difference between these two charges will start decreasing, which means that positive ions will move inside the membrane and neutralize all these anions present inside. This negative potential, if the action potential reaches a threshold, will go to the positive side of the spectrum and eventually it will come back to this state again. So now if this is our membrane, let's assume a stimulus is received. In this current situation, the activation gate is closed. The inactivation gate is open, but it will block the movement of any ion across this channel. Similarly, the potassium channel is also closed. Now let's say a stimulus is received by the cell. It can be anything that will be generated by a graded potential or an external stimulus or any neurotransmitter that is received by this neuron. The membrane potential will change. If it is below the threshold value, nothing will change in the cell. However, if that stimulus managed to depolarize the membrane to minus 55 millivolt, which is the threshold value, some changes will occur in this cell. Now in the previous video, I gave you an example. Like you are sitting on your couch, doing anything you like, you hear a sound and move out of the house. That sound was an external stimulus. What you were doing before was your resting potential or resting state. The intensity of the sound was that threshold value. If it is large enough to make you move out from your couch, it means that it is the threshold. You will go out and an action potential is generated. However, if it was like a spoon or a pen falling, you didn't care. The cell will not care if it is anything below this. So now what will be the change that will occur in the cell? Firstly, this activation gate here, it will open, which means that now the sodium ions present here, they'll start moving inside the cell. As the sodium ions move in, these negative ions present here will start getting neutralized, and therefore the membrane potential will decrease further enough to reach a positive 30 millivolt of potential. These will neutralize. This is what we know as depolarization. The polarity of the membrane is decreasing to the point of positive. So now in this situation, our activation gate is open, our inactivation gate is also open, but the potassium channel is closed. Now this will occur till it reaches a positive 30 millivolts. But now, let's say you're standing out of that house, you'll go back eventually, right? You'll look around, you'll see what happened. Most probably, you'll realize there was nothing much, and you'll go back in. Similarly, this membrane has to come back to its original minus 70 millivolt, which means that its polarity will start increasing now. That stage is known as repolarization of the membrane. Now in the repolarization state, what will happen is that we need to stop this influx of sodium ions. And we have a gate here, the inactivation gate, for doing this. This inactivation gate will now close. And very obviously, this will not allow any further sodium ions to come in. But it's not just that. We don't just need to stop these sodium ions from coming in the cell. We also need to ensure that all these positive ions that are inside have to move out. Otherwise, they might hold this potential at some positive value, but we'll never be able to take it back to minus 70. Therefore, this potassium ion channel will now open, and this will allow all the positive ions inside the cell to start moving out. And they won't just go together, right? They'll take some time. So this phase is known as the repolarization phase. Initially, the cell membrane around this ion channel will start becoming negative, and as time progresses, this entire cell membrane here will become more negative than what it was earlier. So now you're inside the house. You decide to sit down and relax for a while, because it took a lot of energy out of you because of all that adrenaline rush. So you decide to sit down. But you relax a little bit too much and you end up sleeping. Now, your initial stage was sitting on your couch or lying on your couch doing whatever you were. Now your resting stage has equalized to sleeping. You cannot stay that way for a long time. You'll have to come back to your initial position. But similarly, as the cell has done a lot of work now, transfer of all the ions and everything, the resting stage might not stop at minus 70 where it should have. It might, a situation might occur where these channels do not close when they should. The inside has now entirely become positive, but more K positive are flowing out. What will happen is that this negative potential will now become more negative. And this process is known as hyperpolarization of the membrane. obviously the cell will not stay in that position for long, and eventually this K positive ion channel will also close, stopping any further movement, and these channels, the sodium channel, the activation gate will close again and the inactivation gate will open again, and the entire membrane will come to the situation in which it was when it was resting. Let's now plot a graph for the action potential. On the y-axis, we take the millivolts or the potential difference. On the x-axis, we take time. Now the initial resting membrane potential of the cell is minus 70 millivolt. And if any stimulus arrives, this membrane potential will become more and more positive. The threshold value that a cell needs is minus 55 millivolts. So if, say, there is some stimulus that depolarizes the membrane but not up to this mark, these will all be failed. However, if a stimulus strong enough arrives that take this membrane potential to minus 55 millivolts, the action potential will be generated. The potential difference will quickly become positive up to plus 30 millivolts, and this will be the action potential. The phase of the negative going to the positive will be the depolarization phase. Now the membrane has to come back to minus 70. So this will start decreasing. This phase will be the repolarization phase. And as it is decreasing, it might reach the hyperpolarization phase where these channels did not close in time. So this can become more negative than minus 70 and eventually come back here. So this will be minus 90 millivolts, and this part of this graph is the hyperpolarization phase. And this is how our action potential is generated, and this is how the graph looks like. In case of the difference between the graded potential and the action potential, one very important point was the presence of a refractory phase. This refractory phase basically means that if there is a cell that is excitable and it has received some stimulus and it generated an action potential. Now in any of these middle stages of generation of that action potential, if it receives any future stimulus, it will not react to that. Firstly, it will finish what it's doing and then come back to the resting state, and that is when it will generate another action potential. It is the ability of a cell, ability of an excitable cell to not react to any further stimulus while it is producing an action potential. These refractory phase can also be of two types. One of them is absolute and second one is relative. An absolute refractory phase is that period of time wherein any stimulus, no matter how strong it is, will not get any reaction out of the cell. And this will be the phase till our sodium ion channel is not back to its resting state. That is, its activation channel is closed and the inactivation gate is open. As soon as our sodium channel reaches the resting membrane stage, that is when the relative refractory phase starts. Which means that now, if the cell has received a very strong stimulus, more than this minus 55, it will generate another action potential. Now, exactly how this will occur is that, say if there's this action potential that is occurring, the sodium ion channel is in the state where sodium ions are flowing in, the inactivation gate and the activation gate both are open. Depolarization will occur and action potential will be generated. However, as soon as the potential of the cell reaches a state where it is close to minus 70 and is in the hyperpolarization phase of this generation, the sodium channels, they will come back to what they were initially. Therefore, this part of this graph, this will represent the relative refractory phase. Say if the potential of the cell is now minus 70 or minus 60, not 60, minus 85, minus 90, and the cell receives another action potential, it will not go to the minus 70 for a while. It will just generate another one here. However, if the cell receives any form of stimulus during this period, when the cell is already in the middle of the previous potential generation, it will not react to it at all. And in the relative phase, it is very important that the stimulus that we receive is stronger than minus 55. So in case of an action potential, we'll have a refractory phase where a cell or an excitatory neuron might not react to an external stimulus at all, or it might react if the stimulus is strong enough. In the graded potential, however, this does not happen. If there is another stimulus coming in, it will be summed up with the previous one and both of them will act together. This is a summary of how an action potential is generated, the graph that we can make, and the refractory phase of a neuron. With this, we are done with the generation of action potential, and now we need to understand how it is transmitted from one neuron to another. I hope you liked the video, and if you did, do share it with your friends and subscribe to my channel for future notifications. Thanks for watching.